So, hello together. Welcome to the third part of our student series. First, maybe a short introduction of ourselves. I'm gonna activate my camera so you can also have a picture of me. So, hello together. I'm Thomas Eichner from Dlubal Software. I'm working in the structural dynamics department and help in the development of everything that has to do with time dependence, loading, with structural dynamics, as I said, and earthquake design. And I'm also active in the customer support. So if a customer has any questions, I'm always there and happy to help. With me today, there's Paul Silvolgin, and he can just introduce himself.
Hello, my name is Paul Silvolgin. I am a working student at Dlubal Software. I support the product development in the area of interfaces, and today I'm gonna support Thomas and answer your questions in the chat.
Okay, perfect. Thanks, Paul. And now I will start the presentation for you. We can also deactivate our cameras, so you have more place for the presentation. Okay, now you should see the presentation. Yes, we are in part 3 of the series. Oh, okay. Now it should work.
Yes.
Perfect. So we are in part 3 of our student series. It's about the introduction into the finite element analysis, and we can go firstly through the GoToWebinar control panel. So if you have any problems with, for example, sound or the screen, you can just check this question mark here out. There are settings which influence your experience. Also, you can just select your device on which you want to hear me. And also Paul will be ready to answer your questions. So if there will be any questions, you have this field below in this mask where you can just enter the question and Paul will answer during the webinar. If there are any very complex questions, we will answer them per mail. Also for more space of the presentation and the program, you can also minimize this panel with this orange button. So now we can start. You already had the simple introduction into the member design. Also, you had an introduction into our section with the strength of materials. And that's where we are, the introduction in the finite element analysis or finite element method. And in the next 3 weeks, you will also learn a lot more about the specific design of materials, so steel, concrete, and timber. In today's presentation or today's training, we will go through several different topics. First, I will just introduce you in the basic principles of the finite element analysis, which means I will just do a few slides, just the basic principles, so you can remember the stuff you may have already learned in your studies. and yeah, have a better background knowledge on the stuff we will do right here. The next point will be just an introductory example with a continuous slab, followed by, again, just a short theory on the plate mechanics and the plate calculation theories. With the last two topics, we will go on to the nonlinear calculations, so the more complex stuff. Not really hard into theory, but we will show you what RFEM is capable of. And the last thing we will inspect will be the singularities. So one kind of big problem in the finite element analysis. And we will try to figure out how to solve them or at least minimize them. Now I will start a short poll to see who's gonna be able to model with me. This first poll will be, are you working with two screens? Okay, just 50% voted. Maybe a bit more could click on the corresponding answer. Okay, now we're good to go. We can look at the results and see most are just watching for today. But nevertheless, we have 43% who are able to model with me. So I will try to be slow enough for you to follow. Then I'll just add another question. And this is just for me to know how experienced you are. Did you ever have the finite element analysis in your studies as lecture already? Okay, perfect. It's almost 50-50. That's quite okay, I would say. We will go through the basic principles, not too far into detail, but you will know what's going on. Let's say it this way. Okay. So let's go into the basics of the finite element analysis. At first, there are two different methods. There's, on the one hand, the displacement method, where the displacements are the unknowns. And on the other hand, there's the force method, where the forces are the unknowns. For our case, for computer programs and for RFEM, the displacement method is used for the finite element analysis. The finite element analysis is used when analytical solutions of structures are not really possible. That means the finite element analysis uses like a decomposition of the structure into finite elements. So it splits up the model into several squares or triangles, and on each square or triangle it describes the continuum. This means at each border from one element to another element, you have, for example, a displacement in Z direction, and it must be equal. So you have some equations which have to be satisfied. And for inside the element, we have approximations. So there are different approximations and several programs can use different approximations. Also, there's the difference between linear approximations or like third order approximations, which would be a more exact calculation, but also result in a more demanding computer power. The next thing would be the discretization. This is an important term in the finite element analysis. The discretization means that the structure itself is decomposed into these finite elements, into these small elements. And to make it a bit more clear, we have it also in a sketch where I will explain it just simple in 6 easy steps how a finite element analysis calculation is carried out. So the first step would be the discretization. That means we would split up the model, in this case a slab with an opening, into its small elements. And then we would, in the second step, construct the relations of each element. So the stiffness of each element, we would describe it with this approximation functions inside the program and have our stiffness matrix for every single element. To continue and find the final result, we have to transform this local stiffness matrices. That means we have to transform it into the global coordinate system, and then we can put them all together. So we put several matrices together and create a complete stiffness matrix for our system. This is right here, the third step in our calculation. In the next step, we would consider supports and loads. That means the finite elements equation is, it's relatively simple. It's the stiffness matrix K times the displacement vector U, and it equals the force vector F. So with step 3, we got the stiffness matrix K. With step 4 now, we will get our force vector F. And by considering the support conditions, we can also block or strike out some of the equations. Since in the displacement vector, we just set some displacements, for example, to 0. For this case, for this line support, there's a degree of freedom in the vertical direction, and it's completely blocked. So we can just strike out the corresponding entry in the stiffness matrix and the displacement vector. After doing all of this, we can just solve the equation for the u vector, so for the displacement vector, and find our displacements. After having the displacements, we have everything known about the system. And when we know everything about the system, we can continue in calculating wanted results, for example, internal forces or stresses or strains and everything we want to know. Exactly, that would be the 6th step in this case. Now we can just start on modeling. I will just enter RFEM. So if you model along, you're welcome to also open RFEM 6 now. And what we will do is we will create a continuous slab, and we will adjust the mesh size for the same slab, and we're gonna inspect the results. So we're gonna inspect how the mesh size will influence our results. Also, we will compare it to a simple beam, just like one of the easiest structural systems. We will investigate and inspect the problems of the mesh size. So now RFEM should be ready. Not quite yet. But okay. Okay, in the meantime, we can also do just another poll. I prepared one according to the discretization. Let's go. What did I mean with the discretization in the finite element analysis? Okay, perfect. I will close the poll. And the result, it's quite surprising. I never had this before. So 100% of you were right. It's the decomposition of the structure into small finite elements. Perfect. Okay, seems like I had some pushover model open from my dynamic development. These are rather complex systems, and it could result in some loading time. Okay. Now we will just start and create a new model with the new model button on the top left side of our program. We will go with a simple name. Since we are investigating continuous slab and its mesh size, it will be our continuous slab example. We also have the decision to make on which type of model we want to use. The 3D type is the one with the biggest flexibility, since you can just model whatever you want. But to model whatever you want, you also have to respect every aspect of the model. So I will explain this by the type we are going to use today. Right in this 3D model, you see our 6 degrees of freedom. When we switch to our 2D plate model, we see it's simplified into just 3 degrees of freedom. Which means, for example, we don't have to define every every support in the model. The program just supports the whole model in some directions, and that's what we're gonna use today. The 2D XY plate. With OK, the new model will be initialized, and we will get a new completely white screen, just with our global coordinate system at the origin and our complete mesh. Not mesh, let me rephrase it. It's our guidelines for modeling. Since we want to start from 0 today, And the basic program option is to use the materials, sections, and thicknesses from our last model, so we don't have to model them or create them each time completely new. We're gonna just delete all the previous basic objects. And that's done right here at delete all basic objects. So now we are at our free model, and we can either go over this view cube, or we can use these 3 buttons, or well, these 4 buttons to change our view on the system. We will want to look in Z direction from above. That means we will press this Z direction button, and then we are ready to go. We will start by creating a new rectangular surface. It's this button here on top. If you ever used something else, for example, a triangle surface, the triangle button will appear on top. That's just the last used modeling option. So we will go on to use this rectangular surface button. Right here, we can go on and create our thickness. Just for your knowledge, if we don't have a thickness and try to press OK, it will warn us that we have to create a thickness. So the program won't let you do like complete nonsense. It's gonna help you on each step of your modeling process. Now we're gonna click here, and it's gonna automatically start the dialog for the thickness. Now we will go for 30 centimeters, means 300 millimeters, not 3000 of course. And we will continue on assigning a material to this thickness. For the material, we have a few options. We can either go into this library. The book symbol is always a library. And we could filter it by region or material subtype. We could also search here below. Or alternatively, we could just search it in directly on top. That means we will go with the German one. I'm from Germany. That means I'm like only using the DIN norm. It doesn't really matter for C37 since it's standardized for whole Europe, and it wouldn't make a difference to choose something else here, at least for C37. So it should, exactly. It should also implement everything about the materials. So every material properties will be filled out. What we're gonna see is there's also the Poisson ratio. So the possibility of the material to strain in the transversal direction. We will also go on the Poisson ratio later on. But for this example, we want to just activate our user-defined material and set the Poisson ratio to 0. After we did it, we have our material done. We can apply it with the OK button. We have our thickness done. We can apply it with the OK button. And then we can start by clicking the OK button again on modeling our first surface. The first surface will be about 10 times 5 meter. Means I have here my grid points to help me out, and I can just create this first surface. The next point is we want to do a continuous lob. Means we want to have a support on the left side, on the right side, and in the middle of our plate. To create the support on the middle, we also have to add another line. Means we're going to use the new line function on the top right and just go from one middle to the other middle. The system automatically shows us where's the middle point of a line or a slab. So this makes it quite easy. After we did it, we can go out with right click or apply it with right click, and then we just had to close our dialog box. Now we have our first system. We have the stiffness matrix already done in here, like in the K times U equals F equation. We already have the K done. The next point would be the restraints or the line supports. We will use the line support function and just use the predefined hinged one. I will just show you inside the hinges. We had some help with this 2D plate model since it already deactivated us this 3 degrees of freedoms. So we don't have to make 3 button clicks because of this selection. Okay, we can then apply it, and by clicking from the right hand side to the left hand side, we will apply it to every line that is cut with our rectangle. So after this is done, we see we have now our support. We can also adjust the size of our support, and we can continue on. This was in the presentation, I think about step 4, where we block some degrees of freedom. So we strike out some equations from the K matrix, and we also strike some degrees of freedom in the U vector. So now we have the K matrix ready. We also modified it with boundary conditions, and we have the U vector also modified, though it's unknown until after the calculation. And the last part would be the force vector. So for the force vector, we're going to make it simple and just apply an area load of 10 kilonewton per square meter. So 10 kilonewton per square meter. We just have one load case, so we don't have to think about it right now. And we then can assign it either here. We could just enter surface 1. Since we only have one surface, it will be surface number 1. We could select it, or we could just leave this empty, click OK, and select it afterwards. After applying it, we're gonna inspect the appearance of the load. So back in the view from the top, we can see the system. And in the next step, we can just select everything we did and use this button here. This means it moves or copies the selected objects. In this mask, we already see on the right hand side what will happen. The selected one will just be copied or moved to another place. So we want to have 4 plates So we create 3 copies of the system, and we will move them 10 meters. Right, 15 meters. Our system is 10 meters long, and so we want to have 5 meters space in between, and then we want to have the next system. So we will have 3 copies with 15 meters in. After doing it, we will have them right here. And now we see our helping grid is not helping anymore on the last surface, but I need it for the beam, or I don't need it, but it helps me a lot. So we will go into settings for our work plane and grid, and we will just adjust the numbers of grid points. I will just take way too many, like 200, and I will also adjust the grid spacing from 1 meter to 0.5 meter. It's not really needed, but it's possible, so I will just do it. With OK, we can see the result. We have now a new grid, and it's over the whole system we want to go through and inspect the results on. So the next thing we want to do before we model the beam would be the mesh size. Right now we don't have like any specific mesh size for a surface. That means if we calculate it right now, it will just use the mesh settings, the general mesh settings from our result mesh settings, which means our mesh size would be 0.5 meters on every surface. Well, since we want to inspect it in way more detail and have different mesh sizes, we will help ourselves with something called surface mesh refinement. Like said in the name, surface mesh refinement, it seems to be a property of a surface. And our data navigator on the left side is built up very simple. There are basic objects, some special objects, then are the properties of our basic objects, properties of our special objects, something about the loading. So in general, in the data navigator, you could like find each function you also find in the buttons on top. But the buttons on top just help you to be way faster. So, but right now we will go for the surface reinforcement, right here, types for surfaces, surface mesh refinements, and use them. With double click, we can open the dialog and see the first one. We also, in most dialogues, we also have a picture on what is happening within this dialog. So we want to have 4 different sizes of the mesh. So I will go through this and optimize the speed, since I'm just creating 4 copies, and create several different target lengths, one with 2 meters, one with 1 meter, one with 0.5 meter, and one will be very fine with 0.1 meter. Now we have the properties, but we didn't assign them to any surface. So we're also going through the different 4 refinements and assign them to the different surfaces. So the first one with 2 meters for the first surface, the second one for the second surface, and so on. Rinse and repeat. Now, after finishing the 4th one, we didn't like apply it yet. So we can either apply it right here, means now we can see something. I will explain it in a bit. But the positive thing about the apply button is we will stay in the dialog. So if we would have more surfaces and want to have more mesh refinements, we could just go on and create new ones. If you click OK, the dialog will be closed and it will be applied. It would be possible for our case as well. And yeah, now we can also see these squares in our surfaces, and those show us how the mesh size will be. Like this will be very coarse and this will be extremely fine. You could estimate like this will be round about 1,000 more elements than the first one. Means maybe round about not 1,000 more calculation time, but let's say 5 times the calculation time. It's just an estimation. So for the comparison, we will also create our beam. The beam will be done with this button on the top left side. The section will be a new one since we have none yet. So we go into this create new section. We want to have the only material we have already, the C3037. And we want to have, yeah, exactly this rectangular object. The rest here doesn't really matter for us right now. I will go on something later on, but we could also inspect the section properties. To adjust the size of our rectangle, we can go to this parametric massive section. And here we want to have a width of our system of 1 meters, so 1,000 millimeters, and the height of our system of 30 centimeters. We're gonna make it 1 meter since the internal forces of plates are always, for example, one second, I don't want to say something wrong. Kilonewton meter per meter. So it's always for 1 meter. It means to have the same results for the beam as well as for the plate, we need to have 1 meter in the width. We can press OK and OK and go on with the modeling. Now we will just go again and create this 10-meter slab. Well, not slab, but our beam. This beam will be divided since we need and support in the middle. We can just go on and go on this member, go on divide member with intermediate nodes. I could also go on distance with 5 meters, but we will take the more simple method. One intermediate node, very easy. We will also use a new function here, create on member node. I'm just clicking it and pressing OK. Now you see this blue new node. The special thing about this on member nodes is we didn't divide the member. This is 1 member. If we didn't check this, this function, it would be 2 members now. So it's just for more complex systems. You don't want to have hundreds of thousands of beams just because you have like beams coming into another beams and so on. For our purpose, this doesn't really matter and we could go for both options. Now we have this one, this beam, we have our K matrix again. We can go for nodal supports now and add some supports to the system. One problem here is now that we could use the hinged one, the predefined hinged one, but on the predefined hinged one, there's one degree of freedom which we need to block for beams, and it's the physics. So it's the rotation about the own axis. If you didn't do it, it could just rotate and fall over. So after doing this, we have it adjusted right here, press OK, and assign them to all the nodes. Last but not least, we can just add our member load, again with 10 kilonewtons, this times per meter. Press on the slab, again not the slab but the beam, and we're ready to look at this in 3D, since it looks quite cool now. Just a few simple steps and we have our systems. One more thing, we can also do this for loads. We can adjust their size. And yeah, so before the calculation, I want to do two more things. That will be, again, view in its Z direction. And now we will create our, where is it? Our result section. Result section is a special object, so we find it in the special objects. Result section, we double click it, and we just use the basic settings and take our first two nodes from here, from the middle left to the middle right. Okay, we will press OK. Now we can see we have added this result section. Now for better investigation of our loads or of our results, we will also deactivate the self-weight. So we go into the load case and deactivate the self-weight. Now we're done and ready to calculate the system. So we have our results now. We have our results also on the result sections. We can adjust our values to be displayed right here at the values on surfaces. And that seems to be wrong. We have to go result sections, values on result sections. There we can go on local extremes. And that means we just have our results. Now we can see the different shapes and we can compare the deformations. We can see we have here 0.34 meters, 0.34 millimeters, I meant. And we have here on our comparison beam 0.46. So there's a big discrepancy between this coarse model and our beam. This 0.464 seems to be really accurate, but also our not so fine mesh did result in comparable deformations. We'll also investigate this on the internal forces. So we go on the members, the internal forces, and we will look at the moment about the y direction. This is the moment rotating about the y direction for beams. For surfaces, it won't be the my. The my should be 0, but we will go for the mx. Why is it now the mx and not the my? For surfaces, there's a different definition for internal forces. Mx means now we will follow the x-axis. We will cut the slab with a plane perpendicular to the x-axis, and then we will rotate around the corner of the cut. So it's a cut perpendicular to the x direction, and then we will rotate around it. Now we can look again into our into our result investigation. I will disable the loads for here. And now we can see, okay, there's a difference in those one. Also, now I will go into the section result diagrams, right click on the section arrow, then go into result diagrams. And here we can see it already. Now I will, let's see. What's now happening is that we have, I will show it in the general menu since I want to use the 3D. I will also disable the results for what I want to show you. Since we can see now the mesh. The mesh seems to be fine for this right three types. But on the left side, we see it's not quite fitting in the system. We have also a triangle. Just a hint, we want to avoid triangles. We can't avoid them always, but we want to avoid them. They won't lead to the best results. Not completely wrong results, but let's say not the best results. And we also see we don't have an edge of elements now in the middle here. And for a single span beam, we would estimate the maximum moment in the middle. So for this system, let's go back into the results. We can see that here is our maximum on the left side, but it's not exactly where it should be. So the mesh, if it's too coarse, it doesn't only influence the exactness of the results, but also the location of maximums and minimums. And that's what needs to be avoided in any case. So the next point would be which results seems to be fine. So in this case, we will look at the top moment. We have here almost the same results. Seems fine, of course, since it's very fine. But the difference between this 31.35 and this 31.18 is not that much. Means I would also take these results. These results, I would take them as well. I mean, they're really close. I think about 1% maybe difference. But when I go into deformations again, it looks quite different. And that's why I would go for this system here. And that leads to my learned in my studies rule of thumb for the use of mesh size. So I'm going to show the mesh again. So we have like 5 elements right here. And here we have quite more and way more. The rule of thumb I learned was 6 elements per length. So there needs to be 6 elements in the region we want to inspect. That's for design. What I learned in this company is also there's sometimes the possibility for bigger models that you want to design parts of the model and you want to use other parts of the model just for load transfer. And if parts of the model are just for load transfer, 4 elements are enough. Maybe even 3. But however, this one should be avoided in any case. Okay, so now we're finished with our first model already. And the next thing we will do would be some nonlinearity. So what I'm gonna do at first is giving you a short introduction into plate theory, and afterwards we will continue with this model with some nonlinearities. So for the plate theory, we have the analogy to the beam elements. The beam elements, we have on the one hand the Bernoulli beam, on the other hand the Timoshenko beam. The simple difference is the Timoshenko beam also considers deformations from the shear. So it isn't rigid. The Bernoulli beam, the cross section remains in place, same as for the Timoshenko beams, and the cross sections remain perpendicular to the member axis. This is not the case for Timoshenko beam. We can also look at it here. That means for Bernoulli, we have this middle axis perpendicular to the middle axis, the section cut. And for the Timoshenko beam, there's an additional shear angle. Means the shear is also taken into account for the deformations. There's also kind of a rule. The bigger the beam, the better to use Timoshenko. This can be used completely for the plate theory as well. We have the Kirchhoff plate theory and the more exact Reissner-Mindlin theory. We have for both systems the linear elastic material law from Hooke. We have geometrical linear and small deformations. We have that the cross sections remain flat and there won't appear any warping. We have a constant thickness. But for Kirchhoff, we don't consider the shear deformations, and for Reissner-Mindlin, we will consider the shear deformation. For plates, we also consider the transversal and lateral strains. That was the Poisson's ratio in the program. We set it to 0 to have a better comparison to the beam element. We could have also taken just the Kirchhoff theory. For this Poisson's ratio, just what it means. The Poisson's ratio defines the ratio in this equation. Means if you pull a beam and it gets longer, the new volume right here must come from somewhere, right? And it comes from this place here. So the beam gets longer, but it also shrinks in size. That's about the Poisson's ratio. Poisson's ratio is just the ratio of the longitudinal strain. and the transversal strain compared to the longitudinal ratio. So when we will apply this to our plate elements, again, we had no consideration of shear deformations or Kirchhoff, and we had considerations of the shear deformations for Reisner-Mindlin. The main point is Reisner-Mindlin is more accurate, and it's the theory of thick plates. Can be used for thin plates as well, and for RFEM, you can choose it in the calculation settings, but Reisner-Mindlin is the way to go. Kirchhoff is also good for like thin plates, but let's take a Reisner-Mindlin. Next point would be nonlinear calculation. Nonlinear calculation means, yeah, something is nonlinear, right? The problem with nonlinear calculation is we can't superpose stuff. For example, we had in our early studies in statics or mechanics, we had just a dead load case and a live load case, and we just separately calculated them, and then we summed up the results and it's finished. This is not possible for nonlinear calculation. The typical application areas in RFEM 6 or general in the world are, on one hand, geometrical nonlinear calculation. So in German, I think it's first order and second order. And in English, it's geometrically linear and p delta calculation. There's also the theory of large deformations, would be third order. But anyway, we will go for this one. So for second order, the program needs to do its first iteration of calculation. So it calculates the system with its forces on top, calculates deformations, and then it goes into a second iteration. It uses the deformed system, applies the loads again, and repeats the same process. This only stops if the added deformation is smaller than an error definition. Okay, that's for the geometrically nonlinear stuff. Then there's also the nonlinear material behavior. Maybe you know nonlinear elastic material models. There are also plastic material models. And you can just imagine the superposition with a nonlinear material. Imagine you have a dead load case and a steel beam of grade 235. So it can have a 235 Newton per square millimeters. Now you put on a dead load case which just brings it to the limit of 235 Newton per square millimeter. You reach the limit of it. It can't do anything more. Now you also take another load case, a live load case, where you have like the material at 100 Newton per square millimeter. If you would suppose them, you would have 335 Newton per square millimeter. The material can't do it. So it's a wrong calculation. That's just one example why superposition mustn't be used for this. Then there's also nonlinear behavior for objects, for example, for members, hinges, and supports. For supports, for example, you can imagine like a foundation and the ground below. The ground can like stop the foundation to fall down, but it can't stop it from fly away. It won't fly away in most cases, but maybe there's a hurricane, could be. For the next step, we can see nonlinear calculation needs iterative calculations. So more calculations means it's more precise, but it needs more calculation effort. So there's always like the question for you, is it needed to do a nonlinear calculation? And in most standards, for example, Eurocode 2 or Eurocode 3, there are simple rules if you need to use second order or not. If it's not needed, you can just ignore it. On the other hand, computers are getting faster and faster. And for second order, in my opinion, you can almost always do it. But when you combine several points of this nonlinear stuff, it could be quite messy. Okay, that's it. Now I can show you another model, and that's the reactivation. So we have this system here, just a frame of steel objects. And in the middle, we have so-called tension objects. That's a nonlinearity. That means they can't handle pressure. If you pressure them, they will deactivate and they just can't do it. But of course, you can pull them and they will, have tension forces and be able to manage it. So in our system, we have just this frame loaded with 2 times 100 kilonewton. And we can imagine what's gonna happen right now. I will go for theory of first order first and calculate the system. Theory first order, it won't have any horizontal forces. So as estimated, it won't have any deformation in x direction, but it will just be pressured down. We can also see the color of these members. They got gray, which means they failed, they deactivated. So they're just not there anymore, you could say. For this first theory first order, it was no problem since, they are not even needed. Now we will switch to theory second order. And I will just look into, okay, perfect. That's everything okay. And we will calculate it. So theory second order, there will be some imperfections implemented in the program itself. That means it will deform it by a bit to the side and start the calculation. Problem is, we now have an unstable structure. It's movable in the x direction. Why? Well, those both objects just failed. They got pressured and failed out. In reality, though, if the system goes down and then to the side, I'm not sure in which direction it will go, but let's say it would go to the left side. Then there will be a point where this member reactivates again and holds it back, right? And that's what I want to show you. Even though there could be problems with stability, there can be a solution in our static analysis settings. And that means we could go for this reactivation tab. Exceptional handling. And then we will go for the failing members to be removed individually during successive iterations. So they can't fail at the same time in a iteration. We will go for it and calculate the system again. Okay, now we can see we have this model. Yeah, it's stable again since I predicted the wrong direction, but this one is in again, it's activated again. Okay, perfect. Now we can just switch into my next example. Just one thing I wanted to say. Today's webinar won't be 3 hours as intended. It will just last like 1.5 hours, just for your knowledge. We also have the full presentation and the full video of the procedure online. We have everything on YouTube as well as on our website. There's just like RFEM for students, introduction into FEM. That would be the name of the YouTube video. And there can be, yeah, a bit more information about added models and added, added calculations. But now we will continue. By the way, you don't have to model this with me right now. The first model you were able to model with me, but this is just to show you how something working. So now we have a ladder. We have just this ladder and it's land on top of a building on a construction site, and it just stands on the ground. It just stands on the ground means we have here some nonlinear supports. And those nonlinear supports have a friction. We can go into this friction. And now we can see we have, for this translational degrees of freedom, the friction entered. The friction appears here as new one. Could also go here, friction peaks, and it adds on top. We'll deactivate again and go into UX friction. Friction means in X direction, it can take a force which is 20% as high as the PZ force. So when we go into the system, we can see I create some load cases where a person of 1 kilonewton, so round about 100 kilograms, will go from ladder to the top. Now we can calculate the system for a second. And I need to calculate all load cases here. I will also show the support reactions. Now we can see the deformations of the ladder. They don't really matter for us right now. What matters is the support reactions. We have here per support 0.5 kilonewton. Means 20% of the 0.5 would be 0.1. Means the support can do 0.1 kilonewton in X direction. Since the vertical force won't change, the limit value won't change. But when we step up the ladder now, we can see this value rising. This results from the moment of inertia, and not moment of inertia, from the equilibrium of moments. we will go away from the start, and therefore the distance of this moment will be higher, and therefore this force will go higher. Way simplified. And we can step up the ladder and we will see this value going up. And then there should be load case 12. Load case 12, we will reach it. We will reach our limit value. Means at load case 12, at the 12th ladder, for deformation of 30 meters, 40 meters, yeah, the ladder is gone and the person is hurt and crying, maybe. So that would be not so good, but we can investigate such problems with RFEM. What I want to do now is adding a new load case for it. So a load combination in this case. We will add one and go for the linear calculation, and we will add now the last load case. So if the person is standing on the top ladder, and now I want to see why is it said that if someone stays on the bottom on the last step here, or on the first step here, why is it helpful? And that's something we can always also investigate. Therefore, I just need to, okay. And now we calculated it and we can see, yeah, he can stand on top. Why? We have now double force in vertical direction per support. Means also double the allowable force due to friction. And that's why it always helps when someone stays at the first step if the other one is going higher. So then we can go into our next model. And that would be our tension specimen. So we're in a testing bureau. We have, in this case, a surface, a steel surface. It's fixed on one hand, on the one hand side. On the other hand side, we will pull it. We will just pull it. Okay, now we're done. What I did here, we have steel 235. We have a thickness of, I think, 3 millimeters. We have a height here in between of 8 millimeters and here of 10 millimeters. That's why I created a force which results in exactly the yielding force for this section part, for this 8 millimeters height. So this 503.572 kilonewton per meter result in a stress of the surface of 235 Newton per square millimeters. So the limit of the system. I also created another load case where I just increased the load for a bit, just a bit. But it should be more than 235 here then. And that's what we're gonna investigate now. Gonna calculate the system again. And yeah, now we don't have we should have the results. Okay, now we have the results. At first, we're going to look at the deformations. You have here 0.1 millimeter, as well as for this increased load, we have 0.1 millimeters. Go back into this limit case. And now we will go into our equivalent stresses. Our equivalent stresses should be somewhere here. Equivalent stresses. We will use the standard formulation in form of the equivalent Mises stresses and show them. Now we will see some colors. Okay, but we don't know more what does the color mean here right now. Therefore, we go into our control panel. Now we see here. We can see, yeah, the stresses and what each color means. So we see red and orange could be in this yielding region, about 235. But for some better investigation, we can also use user-defined values, and I will go just for the upper limit, 235. Means we can see now we have dark red, everything that is in the yielding region, above 235. Now we see 17% of our finite elements are yielding. And we even have some elements which have 269 or 68 Newton per square millimeters. The material can't do it. So why is it there? I will show you in a second. But first, I will look into the other load case, where I increase the loading for a bit. Now we have 26 to 27% of yielding elements. The rest didn't really change. We also have, yeah, overstressed material. What's the reason for it? We have here material defined. Now we will go into this material with an isotropic linear elastic material. Now, since you're students, you can get a free version of all this RFEM. And the best thing is you can also have all the add-ons for free. And right now we will use the nonlinear material behavior. So I checked it already, and by checking it, it will be integrated in the program automatically. And that's a reason why we can pick here now a ton of new surface models, material models. In our case, we will go for plastic material model for surfaces, for example, isotropic plastic surfaces. The most complex thing is the isotropic damage surface model. There you can just define the model however you want. So we go here for the plastic surface solids model. And within this, I will explain you what we did before. Before we had the linear elastic model. Means we had this here, this E modulus, and this line was tried just linear, just went up to infinity with the same like tangent. But now we change it to this plastic model, which means we have a yielding point implemented and a post-yield stiffness or strain hardening afterwards. This should result in redistributing the forces. So if an element would get like in the linear elastic one, a force of here, this force should redistribute to another element. And that's what we're gonna use now. We have it now and we will calculate it. You can also see there were more iterations necessary. But the point is, now, you see here the upper limit, nothing exceeded the 235. Just a bit here, just a little bit. I think we could change it if we would adjust the mesh size. But now it is as expected. This whole system is at its limit, and it would yield now. Only 1% are over the material limits, which means if they are over the material limit, I will just go into the material again. They are in this region, so they can do more, but they need to have more deformation for it. And that means if we now go into this one, okay, before I do it, I will just show you the deformations again. Just remember we had for the linear elastic model 0.1 millimeter in both cases, and now we also have in the first case for the nonlinear model 0.1 millimeters. But what's happening now? So we go to the bigger force, and we can see now 8.2 millimeters. Means like the 820 times the deformation than we had before. And we can always also see, if we activate the video for here, this Poisson's ratio. You can see how it's gonna get thinner here. So now, in this one, can go here again and look at our yielding, at our equivalent stresses again. And now we see, okay, now we also have 24%, which are over our yielding limit. But they are not much over the yielding limit. It means the force redistributes over the whole height of the system. Okay, so that's it for the nonlinear behavior. And now we can do like another short poll. Choose suitable examples for nonlinear calculations. This is a multiple answer question, so please do not only pick one. Okay, some did vote. So I will close this one and show the results. Okay, just as a hint, every answer was right. So every 4 answers were right. Everything can have nonlinearities. Rods can have nonlinearities, materials, nodes and hinges and supports, and the geometry with this p delta effect. Okay. So What we're going to continue with now is the last part, just a short part of like 10 more minutes. It's the main problem of finite element calculations. And what is this? It's the so-called singularities. Singularities are a big problem since they are discontinuity in the calculation model. So it's not a physical and real problem, but a mathematical problem. Means the results are just useless, kind of. And this can be imagined, for example, at a point load. If you have a point load and you want to look at the stresses in the surface, and you go directly under the surface, you have like no area to distribute the force on. Means you have infinite stresses. And the further you go away from this central point, you will decrease the stresses. Also a problem, the mesh refinement does not improve the result. It's the other way around. A mesh refinement will most likely be more harmful to the result, since the nearer you come to the point, the higher the result gets. Some typical locations are point loads or point supports, nodal supports, line supports, ends of line supports, also openings and corners of walls, also ends of walls since they act as line supports, and jumps in stiffness, for example, due to material or thickness. That's all already for the singularities. Now I will just go into the model and go over one last example. Now I will just model this and show you how to speed up your modeling at first, and then I will show you how to treat with singularities. Means we have here right now surface with C2025, a thickness of 300 millimeters. That's okay. That's the pre ones from the last one. Then we go for, what do we do now? One second, I had something in mind for it. Eight times 6 meters. Exactly. That's what we do. Next step, we will add
Okay, seems like Thomas's presentation interrupted. So maybe I can sum it up for now. And yeah, I think I don't know if I have the right to share my screen. Yes. And yeah, also for this training we talked about the basic FEA, the model. We modeled a continuous plate with area loads and compared views and surface elements. We go through the plate theory of Kirchhoff and Eichner-Mindlin and looked at some non-linearity examples. And at the end, Thomas talked about the singularities and his PC shut down for some reason. So I will sum up or end this presentation for him. And at the end, you will find the full recorded presentation online and also training on our YouTube channel. Also the training from the last year. It's nearly the same. So it's already on our YouTube channel. And if you're interested to test the software for yourself, you find on our website under education a free software for students. You will get the full software for free with every add-on and also for steel, timber, concrete design and so on. And also feel free to check out our website for other trainings and courses, and also we offer big service for support and also for the education. We have a big knowledge platform, online manuals, we have knowledge bases, we have frequent asked questions. If you have some problems with your model, you can also always contact the customer support also as a student, completely for free. And Thomas just write me that he could continue in 20 minutes. So I would say we make a break for 20 minutes now, and if you're still interested to see the full presentation, we will continue in 20 minutes.
So, hallo zusammen. Perfekt, da bin ich wieder. Okay, perfect. I'm back now. Sorry for the interruption. But now we can continue with our training. Just since I'm a bit aware that there was a longer break now, I'm just interested in what you did remember from the first part of this training. By the way, I said earlier that the meeting will be a bit shorter. This won't be the case now. I'm sorry for all the circumstances you're going through right now. Just to say it out, my laptop accu went down and I had to change my place. So now we can go back to the poll. I will show the poll right now. And now you should complete the sentence. DFE mesh size should be A, as fine as necessary, but as coarse as possible. B, as coarse as necessary, but as fine as possible. or C, as fine as possible, but as coarse as necessary? Okay, I will just let this poll open for like 2 minutes, since I see it will be a bit for you all to come back, since the end of the break was not like, yeah, overseeable for you guys. Okay, perfect. Now I see there are some answers. And now I can show the result. So there are 75% who did pick B. Well, but it would be answer A. So as fine as necessary, but as coarse as possible. This relies in the fine should be as fine as necessary, since if it gets finer, it's computational demanding. But it should be as coarse as possible, since, okay, the other way around. It should be as fine as necessary to achieve the, yeah, exact enough results, but it should also be as coarse as possible to have the least amount of calculation time for it. Okay. So now for the last two models, they shouldn't take too long. So if you want to, you can start, and I will create them from zero again. If you want to, you can model along. And yes, so let's start by deleting all the basic objects again. And then we're just gonna start now on the left side by creating first our material. So I'm gonna double click it and start by creating our concrete of grade C30s 37. Now I will use a Poisson's ratio of 0.2, so I won't adjust this and do it with OK. So now we see we have here one material. The color of the material is blue right now. This means the material is not used in our model. And in the next step, we will create our thickness for the plates. This would be again 300 millimeters with the C30-37. So now we have also a thickness. The thickness is now blue because it's not used. And the material got now the black color since it is used for our thickness here. So in the next step, we will create our first surface. We will do it again with this rectangular surface. And we'll go for this 8 times 6 meters. Okay, so we have our surface right here. By the way, by double click on the middle mouse button, you will center around the whole model. In the next step, we wanna just set a point out in the middle of our surface. That's what we're gonna do next. We just create a node on the middle of the surface. And that's the point where our load comes at. So we go on nodal load and set here like 10 kilonewton. Or let's say 100 kilonewton. Let's make the results more obvious. We will do 100 kilonewtons and we are gonna set them on our newly made node in the middle. There would be also another possibility with this free loads, but I will show a free load later on in the next model. And it's kind of the same amount of work to get to the load in the end. So we're good with just this procedure. Next thing would be we just do easy line supports on each corner. Therefore, we use our predefined line support hinged and select all those corners, all those edges. Okay, so we're done with the surface. And in the next step, we would do, like in the first model, the option to copy the selected objects. We want to do again one inspection for the mesh refinements in the end. So we want to have 4 surfaces with 4 different mesh refinements. That means now we had 8 meters in length. So I will displace them by 10 meters. And the amount of surfaces I want to create is 3. Input those values and click apply. And now I see I did something wrong. So I will go back, press Steuerung Z and do it again. What I know is I worked with our specimen model before, and there we had everything in millimeters. That's why we have millimeters right here. But everywhere there's an input of length or forces or whatsoever, we have this button here below. It's our unity button. And with this unity button, we can change our lengths and say, okay, I want to enter them as meter. We could also adjust the result exactness. So how many decimal places would be in there? But it's not of concern for us right now. So we will press OK. And now we have the right unit here. Now we can take 10 meters 3 times, click apply, and we're ready to go. Now we see I did press apply. So we stay in this. If I would press apply again, I would get 3 more slabs on the right. Also, if I press OK, I would also get 3 more slabs on top. So in this time, I will go for the cancel button, since I don't want any more slabs. Now I see again my grid is not around the whole model. That's why I will go into this adjustments for the work plane again. And since I'm not gonna model any more things, I will just go for this dynamically according to size. And we will see what it's gonna do to our grid. Perfect. It's just gonna adjust the grid perfectly to our model. Now there are 3 more steps. The first step is the mesh refinements, same as in the first model. The second step will be the section, so this special object of result section through the surfaces. And the third step will be the deactivation of the self weight. So we will start with our surface properties. So we go into types for surfaces, and there we go into surface mesh refinements. With this done, we can just go for 4 new mesh refinements. The same ones as in the first model. And we will assign them. Okay, now I'm at surface mesh refinement 4. So I want it to be at 4 surface. Perfect. And then I can start from top to bottom, because it's a bit more obvious. Okay, so every surface refinement is assigned. We can click OK and inspect the size again. Since we did that already, I will just go on with our result section. So we go for a special object, a result section, and create it via double click. We can select the leftist middle corner, middle point, and the rightest middle point, and just click OK, since our basic settings are okay. So now the model is completed, and the only more thing I want to do is to deactivate the self weight in our load case. This is done. We could press calculate again here, but I will just go for OK. And then there are different possibilities for the calculation. One would be the calculate button. You could also choose if there would be different load cases to just calculate one load case. And the other possibility is just to select show results. Since there are no results, it will start the calculation to show you the results. Okay, so now we're in the model again. For the deformations, it doesn't look that bad. I will show every deformation value. So this seems not to be an issue for deformations. But when we switch into our basic internal forces, and I go for the mx again, so I cut, like for example here, and then a moment around the corner, around the edge, and we go for it, we can inspect something disturbing. Now we see it's not the best result, but let's say that the most coarse refinement will lead us to the lowest result. Means if you design now for this value of 37, you could be underestimating the internal forces. And we can inspect 37 to 61. There's almost like a factor of 2 between those. So that's a real problem, since how should we know how much reinforcement we should put in that area? How should we know how to design this singularity? And now there are some like tools for engineers to help yourself. Since you can, for example, you could just say, yeah, this is a singularity and this won't happen. Sometimes it works that way. For reinforced concrete, if you have a column on top or below, you would do a punching check, which treats the singularity. For this case in here, we have a nodal single load. So we could do a punching check. It's called, I think, an indirect punching check. But we could also try another thing. And that's what I'm going to show you now. We can go into these sections. So we go into right click on the section, into the result diagram. And here we can see the problem again, but we can adjust it. And that's, I think, the third button on the top right. Yes, this it is. And I will just let it open now. I will just enter the values first. So if you're modeling along, you will have enough time to copy them. And then I will explain what they mean. So okay, what this means is we are smoothing our results now. So for example, a nodal load, in most cases, you don't have a real nodal load. You can imagine like pressing your finger with your other finger. Okay, that's like a distributed load on. But a nodal load would be more like a needle, which you like, press onto your finger. And it's rarely happening on buildings. So when you have a column on a slab, you firstly model it just with a point load, just because it's simple. But in reality, it stands like on a square meter or 0.5 square meters, and this point load is distributed on this surface, on this column section surface. So that would be a thing. And in this case, I'm gonna make it simple and say my column on top is 1 meter times 1 meter. That's one extreme. It's not normal. Most are 30 centimeters times 30 centimeters. But we're gonna go for 1 meter times 1 meter. So I will now smooth the results in a range of 1 meter around the centroid point. That means for the first slab, we had our point line at 4 meters. This is why we end at 3.5 to 4.5. And so on. We also did this all for the other 3 slabs. Now I will press OK. Then we immediately see our results. We can now see this pointed line here below. We have now another thing. We could put this in our printout report. We could put this in our static document and say, okay, we have our system here and we will design with this value. You can see 30.8, 31.7, 30.8. So they're almost similar. The only problem is if you get to fine, it really creates problems here. You see how, that there's a difference of, I think, 15% here. And you can also see the biggest value was 61 here, and it was lower in the rest of the example. But for the smoothing now, it's the other way around. So there's kind of a limit for the refinement. Shouldn't go too fine in your model. That's one option for your model to treat singularities. In general, especially in reinforced concrete, you will put, let's say, 11 square centimeters per meter. Yes, so it's per meter. So in reinforced concrete, forces mostly are able to redistribute because there is a lot of safety factors in the calculation and they don't come from nothing. So there's space to redistribute forces. That means when you locate your reinforcement with square centimeters per meter, you can always, not always, in most cases, you can inspect the results on a meter, and you can mostly smooth the values on a meter. Okay, so that's one possibility with the smoothing ranges. The next possibility is, like I said, we have a column on top, so it should be an area which loads the surface, the slab. So what we can do is create a new load case. I will just rename this in nodal load and copy it. And then I will now make an area load with the dimensions of our column. Therefore, I will just delete this whole forces we have already. Go into our set view again. And now we have to use the free loads. So we will go for a free rectangular load. The positive thing about those free loads is you just need a surface to assign it on, and you don't need objects to create this load. So we can go for the center and the sides of the rectangle since we know the center already. We could put in our x and y coordinates by hand, or we could just pick this node, and it's way easier. So we don't need a node, but it helps. The next point would be to define the edges of our column. It's 0.5 by 0.5 in this case. And then we will adjust the load. So we had 100 kilonewton point load. And now we want 100 kilonewton on 0.45 times 0.5 square meters. Means 100 times 2 times 2, we have 400 kilonewton per square meters on this 0.25 square meter. We press OK. And select our surface. It's this one. And press OK. And it's done. So now I see, or we see that we are back into our program, back out of the force dialog, and we need to open it again. So that was kind of, a few clicks too many. What we can do also is we can click the second surface here in the dialog, press OK. So this was not with this OK here on bottom, but with this top assigning. Then we can select our new middle point, so this one, and then we can click apply and next. That means this area force is made and we stay in the dialog. So we can just go on with the other two surfaces without having to click 2 more times. So it's always changing this surface assignment and picking the new middle point and apply and next. The same thing one last time. Okay, now we can press OK since we don't have any more surfaces to load. Now we have our surface load. You can also see it right here. And we can create the calculation or start the calculation. Okay, and now we can see the results are way better, right? So we have now this 33 kilonewton meters per meter, and the only black sheep kind of is this on the right. You can see 27. I won't do this right now, but if you inspect this curve here, you can also see we have more of a triangle right here. But right here we have a parabola. And the surface under a parabola is more than the surface under a triangle like this. So if we would do the smoothing of results again in here, this would be more equal to each other. So a combination of both is also for special cases possible, but it always depends on the effort you wanna put into singularities and how much of a problem you see in the singularity. Okay, so this is it for point loads, and now we will get into our last model we can model together, and that's gonna be a singularity at nodal supports. So we will go for a new name, singularity nodal support. Press OK. I will go now for the 3D model. I forgot it, but we'll just go for 3D model. It's okay. And we're gonna do almost the same model. Again, 4 surfaces. This time we will go, let's see if we have thickness already with the right thickness. Yes, it seems right. So we don't have to create a new, we can just take the one from the last model and create our first surface. Okay, this time I wanna now, okay, I will go out of this dialog again. I wanna now go in this Z view via cube. So I will go on this cube and press on this plus Z. You can also like throw around your cube however you want, but we will stay in the Z plus direction. Now we will create again a surface, like I said, with the predefined ones from the last model, and go this time for 8 times 4 meters. Now we will also add the location for the nodal support, and this is gonna be at 2 times 2 meters. Okay. Next thing is we will create a line support on the right side, and then we will create a nodal support in the middle. So I will go for this line support right here, and the nodal support right here. Okay, it's not really kind of seeable, so I will adjust the size for a bit now. Okay, for forces we're just going to be simple and take again 10 kilonewton per square meter on the whole surface. Looks all right already. And then it's time to copy it again. So this time we're going to select everything and just right click here. Then we can go here on the manipulation. There we can see our move and copy button. We'll do it and just create 3 copies again in I think 8 meters for this again, so we make 10 meters again. And we're ready to go. So now, as always, 3 more simple steps. The types for surfaces with those surface mesh reinforcements. I will just do this real quick. 2 meters, 1 meter, 0.5 meters, and 0.1 meter. The assignment to the surfaces. So we have our surface refinements and can go on with our special object of the results section. Just again, it's like exactly the same section as in the previous models. Okay, the last step, we can deactivate the self-weight. It doesn't really matter, to be honest. I mean, these are 30 centimeters plates. So I think reinforced concrete has 25 kilonewton per cubic meter. 25 times 0.3. It would be 7.5 kilonewton per square meter extra. So yeah, it would be just 17.5 loading instead of 10 without the self-weight. That's the only difference right now. So we can calculate it now. And then I will go in the other direction again. Well, it's way cooler with this button. And I want to have the local extremes as values again. Okay. So the first model was garbage all the time. Because you see just one element on the left side, 3 elements here. It's just not enough, so we can ignore this. For the formations, it seems like the singularities are not really there. So singularities do not really affect the formations in this case. There's also a different method, as mentioned in the beginning. We are now working with the deformation method. You take the other method, the unknowns are not deformations but forces, so also the singularity meaning changes. But right now, and for most programs, almost all programs, you will have the problems in internal forces. So we go again for the basic internal force mx. We can again see here there's a jump, there's even a jump. So this is, don't use this coarse net. And on the right hand side, we can see the same as for nodal support, for nodal load. In the end, such a nodal support is very similar to a nodal load, so we could expect it. But here are now different possibilities. And one of those possibilities to treat it would be to go into your nodal support and adjust it for a bit. Right here, you can see now there's the possibility to enter spring constant. This means we want to have one in Z direction. So I will deactivate this. And then there won't be a fixed support in Z direction, but there will be a spring support. So I know the result already. I will just go for 700 because for this model it doesn't matter. It doesn't really matter. It makes just a small difference, the value in here. I will go for apply. Also, we see already our nodal supports changed into a spring in Z direction. And then we can calculate it. So now we're back here and we can see, yeah, it didn't really help, right? The problem with this kind of help is if you want to use like springs there shouldn't be a defined, what's it called? Statically defined system. Right here, we have a line support here. So this surface can freely rotate around this line. The only thing that stops this surface is our nodal support. That means whatever we do to this nodal support, it has to take everything. So the force can't go somewhere else. The only different thing now should be this. You can see this here. This is now the deformation. That means this one goes 40 centimeters. It moves 40 centimeters downstairs. So, and we don't have this like belly in here. So it means it takes all the force again, but it deforms differently. Since we have a very small like spring constant right here, 700 kilonewton per meter. Could also calculate it, I think. Yeah, just taking the support reaction divided by this, and then we have the deformation at this place in the end. Okay, so for this case, it won't help. For bigger systems where you have walls, and especially if you have a combined system of columns and walls, and you have modeled your columns as fixed, then you will have lots of singularities. So in the praxis, for especially reinforced concrete, there's sometimes for special models, well, not two special models, just mid-size models. You would create two models. One where the columns are stiff, and one where the columns are, springs, kind of. And then you have two extremes, and then you would do some constructive thinking on where in between your solution would be expected. You can also just go for the spring constant value, but here, like I said, there are a lot of insecurities in material, in everything. That's why there's this factor for concrete of 1.5, so 50% safety factor for the material. There's a lot of space, let's say it this way. But most of the time, if you use a C2025, you will get a C3037 anyway, because the production company sees no difference in it, and it's cheaper. And it can more. But in special cases, it could be bad. So yeah, it's helpful to think about this sometimes. Okay, so the next thing we can do to treat such singularities from nodal supports is, we can see it here, we can create a stiffness via fictitious column. Yeah. Now we can't edit them anymore, but we can see here what is going to happen. We now have our column, the nodal support. As for a point load, in general, there's almost never like a needle holding a slab. It's almost always a column with a size. Mostly, I think the minimum size would be 18 centimeters by 18 centimeters. For Germany, you almost never go below 22 times 22, I guess. So we can also just take this into account. And the program helps a lot with this. We can just enter our estimated story height. In general, we know it. This is 3 meters right now. We can say the dimensions of the column, 0.5 times 0.5 meters. It's again a really big column. I think the biggest one I saw was 0.4 times 0.4. But also we have not so many like skyscrapers, so that's mainly the reason why I didn't have to plan much more. And yeah, now we have everything defined. We will go, there are also different possibilities. We will go with the elastic surface foundation as depicted in this figure, since it's just the best result. Also the stiffness here, I will go again to 5 again. You can also just see the stiffness values, which are calculated from all this information automatically, and how they are changed right after your number insert. Okay, we will press OK. This will delete our results, of course. OK again. And now we can calculate this model. Okay. So we are back again and can watch our results of our moments. So now we can see we don't have this region where this column is standing. That's okay in most cases, especially for reinforced concrete. You design with the moment at the end of your column, so exactly this one. Generally, you shouldn't calculate with, if you have a cantilever like this one on the left, you should take the moment in the middle. So for cantilever, this option would not be the best one. You could go a different way by using one of the other options in here, like these two. But for this case, we will just say that's not a cantilever. Okay, so what we see here, we have a bit of better results since we don't have this 110 value or something here on top. But we can see also differences in those values. So that's like hardly to interpret. What I was doing when I was planning buildings is I would also look at this field moment. You see, this is really similar to this, and that's also not big of a difference. It's just a difference because we don't have a element edge or yes, right here. So we have here again the wrong location for the maximum. But then we could think about, okay, QL quadrate divided by 8 or something like that. And we could also think about, okay, we have here like, this could be a fixed support. We could say we have here the cantilever and here it's just fixed. And we could say via our general formulas, for example, from the Schneider Bautabellen, and think about, okay, what's realistic for the value here. Then we could inspect and look which size would fit this result the best. Okay, so that would be the procedure for singularities. And now I have one finishing poll. The last poll for today. And it will be, where do singularities occur? It's very similar to the last poll. Multi answers are possible. So maybe the first one just selected one. I'm not sure if you can adjust it afterwards, but it was fast, let's say it this way. But just as a tip, your one answer was right. So maybe one last click on here. Okay. I will close the vote and show the results. So in this poll, everything was right again. Like singularities can be at re-entrant corners. So corners of two walls which come together, nodal supports and concentrated loads. We just made two models for this. Then also in a jump in stiffness, material or thickness. Yes, it's just a jump in this. I mean, we had in the beginning this formula k times u, and it's just a jump in the k. So it's a jump in the equation. So there will be something strange. And at the beginning and the end of a line support. Yeah, because in the direction of this line support, at the end of the line support, kind of it almost acts like a nodal support. Yes, so that was the last poll here. And now I will show you just one more interesting thing on our website. And that's like we have, as I said, you can get this software for free as student. You can just check out all your exam questions and calculate them with RFEM to have a comparison result. You can have lots of trainings. In here we have this cool, let's say, where was it? Handbücher and videos. Just like the videos are just like the video we did right here. You can inspect it on YouTube or on the homepage. You can just find it over this platform. Also, you can just search for, yeah. Oh, okay.
I think we still the survey. Maybe, I don't know if it's done for me.
Is it now done?
Or I still see the survey only.
Okay, I had the problem in the last one as well. I need to now it should be better, I guess. Is it working now?
No, it's still only the survey visible on my screen. Now I see your screen, yes.
Perfect. So we are on the Dlubal homepage right now. And there we have this Bildungs button. Wait, I can just switch into English. We have the education, and there's this free software for students. So right here, you can just like compare student thesis or like tasks in your studies, or yeah, test calculations. You can all make them with RFEM and compare them and have the exact results for it. Also, there will be, I just have to look for it. That's the best thing about RFEM in my opinion. I will just go here. You have also, for example, this is something about reinforced concrete. You have also for every check on every location, you can just go in and get all the equations. So for your test examples, you can just go into the program, make the model, and then you have the check perfectly aligned. You can just check your own calculations, what's different, where you did the mistake, on which step, because in many cases in the tests or the given results of the tests, you only have the end result, right? And with this, you can try to figure out where you did the mistake. And that's new in RFEM 6, and it's really great. So you can just use this in your everyday study. Exactly. So back on the homepage, what we also have is if you do a thesis with RFEM, you will get $150 Amazon Woche. And you will get also, I think, a book, but I'm not sure right now. However, what you will get, and that's way more worth, you will get a 6 months all add-ons version of RFEM, inclusive the Surface contract. That's way over $50 dollars. You could look up the price right now. I won't show it in here now. Yes. The next three trainings will be more detailed on the design in reinforced concrete, then steel, and then wood or timber. So check them out. There you will find this printout I just showed you, where you can compare your tests better. And okay, that's like all from me. I'm really happy you stayed this long in the end. I mean, it was an up and down today. So my, let's say, honest thanks to all that are still here. In the end, when I close this, there will be just a small survey on how cool you think this training was. Just to be clear, 1 stands for really, really bad, and a 5 stands for it was great. So that's all from us. And then we wish you a nice day and a nice rest of the week. So hope to see you in the next training. Bye bye.